Welcome back. This is part 3 of lecture 24, and this part is about response surface methods. Before we move on to the two examples, I want to say a few more words about canonical analysis, primarily because in the first example you'll see how this is used. So remember that by canonical or normal form, we're referring to a representation that's scaled or dimensionless. We're not working in the original units of the factors. That's what we mean by the extrinsic coordinate system. And that we're developing a method for finding these stationary points or the points of interest, be they maximum, minimum, saddle points, or along ridges, in a way that's independent of the units of measure or independent of the original phenomena. So very briefly, without a lot of time, here's a second order model. It's in the extrinsic coordinate system. I can see that by the representation that I'm using: response variable, intercept, first order terms, second order terms here. Rather than independent variables, be they 2 factors or 3 or 4 or more, we're using this matrix vector representation. And when I see a term like this, we know it's the first order term, and x transpose bx represents the second order terms. Now we're moving from an extrinsic to intrinsic representation. It's one thing that's happening. And I'm doing that in 2 parts. One is by locating a point with respect to the lower bound, and you'll see that here, xi minus xi0 is subtracting the lower bound from the original value. So if it was at the original bound, then I would have 0. If it's at the upper bound minus lower bound, be at the maximum value. And when I multiply it by the eigenvectors, I'm then mapping or transforming that into the intrinsic system. So a upper bound minus lower bound would be mapped to a value of 1. Now, the one thing that I mentioned, but I wanted to reinforce, here's our model in the intrinsic coordinate system. And I want you to notice one thing, that this representation does not have the first order terms. This has purely the intercept term and the second order terms, right? Some of the second order terms, but not all. Right? So the full model of the first order terms plus the complete set of second order terms would be very, very large. This is just a representation as an example where these are intrinsic values of the response variable, intrinsic values of the factor values, and the intrinsic values of the regression coefficients turn out to be eigenvalues. Okay. And I mention that briefly because when we get to the last example here that we ended the last part of the lecture with, I made the comment that this is a model where it sure looks like the stationary point, if it's a maximum, is up out of the region of interest, right, bounded by A and B here, and here's the value of the response variable. And to get out here, we can't just use the second order terms, so it might be helpful to fit the model with linear terms, the first order terms, which I did not show you in the example 3 slides before. Okay? If it's simply a model like this ridge, or the saddle point, or the maximum, then you don't need those first order terms. You simply need an intrinsic model that's like the equation you see here. This is the value of contour plots, because you see, if you see something like this or this or this, you're okay with that purely second order. If you see a model like this, where the response value is increasing, but the maximum or stationary point is outside the region, then you're going to need to add the first order terms. But let's move on now to an example from the R package RSM for response surface method, and then we'll move on to a brief example that's from the literature. So the first thing you have to do is to load the RSM library, using the command that you see here. If you haven't done so, I'd recommend that you do it, and after viewing these slides, you might want to try this on your own and maybe explore making some different contour plots or explore a different model. So we first load the library, and when you load the library, you'll be loading not just the functions that you'll use in R, but it turns out that there are some data sets within the library that you can use. And the one that we're going to use in this example is the helicopter data set. It's a data set HELI, H-E-L-I. And it's an experiment with paper helicopters in which there were 4 factors and 2 blocks. Right? And then both will become important when you see the model. 4 factors and 2 blocks. The experiment was done with a central composite design. And the 4 factors were the following: the wing area A, the wing shape R, the body width W, and the body length L. Those are the 4 factors. And there were 2 blocks. And the goal is to make the helicopter fly as long as possible. So the response variable would be time, say. And you see that I could ask a question: does variation in the wing shape account for the variation in time? The classical experimental design. Or I could form a regression model: does wing area and wing shape, or is there an interaction between wing area and wing shape that explains the variation? But now we're interested in a slightly different kind of question: is just what is the optimal value of these 4 factors, wing area, shape, body width, and length, that optimize the time in which this paper helicopter will fly. Each observation in the data set is a result of 10 replicates. So I encourage you to load the library, look at the data set, load the data frame, and take a quick look at it. The information that comes along with it, the documentation for this data set is just more detailed than you'll find here. But suffice it to say that each of the observations that you have is 10 replicates, right? So there were 10 repetitions, and they were averaged to form each data point in the experiment. So the data frame has average flight time, which is called AVE, and the 4 factors. Now what we're interested in is a response surface model using a second order surface. So here's the R code that we start with. The function is RSM that we use to estimate the response surface. I'm saving that in an object called HELI, HELI.RSM, and the model that you see is that the average of the flight time depends on block. Remember, there were 2 blocks, and SO means second order surface of the 4 factors, right? And much like linear model or analysis of variance model, you specify the model and then the data set. Model, data set. So the same structure of the arguments. Here, average flight time depends on block and a second order surface. That's a function of the 4 factors. And here's the data set. So step 1 is to generate that object. And here is the summary, and you see that printed. Here was the call that was made. So this is part of the history. That's part of the object. And then here are the residuals. right, of the residuals after the fit. And you can see the range. You can see that it's roughly, roughly symmetric. It's not, it's not exact, but it still looks like it's a pretty good fit. Next part you see are the coefficients of the model, and so there's the intercept, right, where it was beta 2, or we called y0. There's a coefficient for the block, since that was part of the model. And then here you see all the terms of the second order fit. So the second order fit in this particular case doesn't mean that it was the first order terms were excluded. When we say second order in this sense, and using in the R library, there I have the first order terms, the interaction terms, which are second order, and then second order in each of the factors by themselves. So 3 parts: first order, interaction, second order terms. Here's the estimate. And of course, we're interested in the probability that these values or the probability that these values would occur under the the assumptions of normality that be greater than the t statistic here, right? So what appears to be significant is x2, wing shape, x4, I think was body length. Here are some of the interaction effects, right? And second order terms such as x3 and x1 squared. Right, so there's a second order component, there's some interaction terms, and then there's first order terms that appear to be significant. So the likelihood that the flight time is independent of all of these factors is very, very small. That something other than randomization gave rise to the observed behavior, and that this pattern would suggest that some of these terms, linear and second order, would explain that variation. Here's another part of the summary that's important for us. So the response value is average. So this is the analysis of variance. One of the components or pieces of the pie is the block. Remember, I had 2 blocks, so there's 1 degree of freedom. And the probability that that F statistic is greater than the critical value is 0.2, so that's not significant. This means first order terms. Then there's the purely quadratic terms, PQ, and then there's the 2-factor interaction terms. Right, so what appears to be significant in terms of the observed variation is that the observed variation of the flight time may be explained by the first order terms and the 2-factor interaction, but also the quadratic terms is significant. Just the probability is much, much less that this F statistic could appear just under assumptions of normality. So this is an example of how one might use response surface methods. Okay, but that doesn't tell us the operating conditions. That just gives you some idea that there is relationship between these factors and the observed response variable. Okay, so now comes the analysis part, right? I mean, what you saw to date, or just in the previous 2 slides, was the analysis that we've done before in terms of t statistic or location parameters, or the analysis of variance in terms of the observed variation. But remember back to the previous section that the analysis for response surface method is done in two parts: graphical, which is the contour plots, and the eigenvalue eigenvector or canonical analysis. So if you continue through the summary, and again I encourage you to run this on your own, the next thing that you'll see is the stationary point in the response surface. So here's the stationary point. We don't know whether this is a maximum or a minimum or a saddle point, whatever. But here are the four factors, representation of the four factors, but in the intrinsic coordinate system. And here is the location. So the one is positive and the other three are negative. And here's the stationary point in the original units, right? So this is intrinsic, extrinsic coordinate system. And here are the eigenvalues. So we see one is positive and the other three are negative. All right, so that should tell you something about the surface. Now I'm not going to give this away completely. I want you to go back maybe to your notes or to the previous portion of this lecture and look at the last few slides to determine whether the signs suggest that this is a maximum, minimum, or a saddle point. The portion of the RSM object below are the eigenvectors, which really indicate the directions of the maximum and minimum variation in this four-dimensional space. So again, go back to the previous lecture, determine what this means, and be sure and be ready to discuss this next week. Now we'll also want to look at contour plots to give you an idea. And here's the code to generate some of the contour plots. This is not done automatically from the RSM function. This is a couple of additional lines of code that one would use. Right, so the first line is partitioning the graphical print space into a set of 6 plots. That's 2 rows of 3 each. Right? The graphical space is partitioned, and then the function contour is used to generate the contour plots, and you see the lines of constant flight time as a function of the variables that are on each side. So in the top row, the x-axis is the variable x1, which is the wing area. In the bottom row, the variable is x2 in the first 2 cases and x3 over here. And in the top row, this is x2, x3, x4. And then this is x3, x4, and again x4. Okay. But let's take one of these as an example. All right. So you see here, this contour where I have the mouse is 375, 370, 365, 360. So the maximum is in this direction, so it's toward a smaller value of x1, and a larger value of x2. This is x1 and x3. Right. And if I move over to the second plot that shows the contour relationship between x1 and x3, you see 370 is here. This is 365, 365, 355, 355, so that the maximum is somewhere within this region of x1 and x3. Now we know that it's down here, so the value of x1 is somewhere closer to maybe -2. It's likely then that the value of x3 is similarly large at the maximum point. And here you see a more complex structure with x1 and x4, 390, 380, 375, 70, and then it decreases along this way and decreases this way. So this appears to be a saddle. Right, so you see contours here and contours here, and then a maximum here. So the x1 is towards -2, which we see over here, but that x4 at the maximum is probably in that range as well. Right. And here you see where the actual response surface stationary point is. Now, by my graphical analysis, you see I wasn't anywhere near close to this. I mean, I thought x1 was, was a large negative, and x3 was a large negative, and that turns out not to be the case, which is why in the last section I was suggesting use this first, get yourself close, right? And then you'll optimize further. Okay, well, this gives you some behavior of where you might be operating. Okay, right? You look at this two alone. You can't take into account these two factors. You might think that x1 is going to be x1 at a stationary point will be a large negative value, as I would over here, but see from the analysis it turned out not to be the case. So if you're using the RSM library, rely on the numerical results which you have at your disposal. I still encourage you to do the contour plots to be able to look at pairs of variables, pairs of factors, because that'll tell you something about the interaction, not necessarily where the stationary point is. So in a case like this, where really a 4-factor problem is relatively large by the kinds of things that we've looked at this semester, that you want to rely on the contour plots to give you some idea of the relationship between factors, maybe the second order properties, really the 2-factor interactions, but rely on the canonical analysis, the numerical analysis you see here, to give you the actual results, where the stationary point is. And again, this is 4 dimensions, so think about whether what we're looking at. Now you know that we're interested in the maximizing the flight time, so you probably can guess without too much trouble that the stationary point is going to be our where the maximum is. Then from the model, the actual magnitude. Right? But we still don't know a whole lot about that 4-dimensional structure because they're hard to visualize. And as you see, 2-dimensional plots will only tell us about the interaction. So we really ought to think about 3-dimensional plots here, or sets of those. So that's example 1, which I encourage you to run on your own. It is the paper helicopter data is part of the RSM package. At least run this one and see to make sure that you can reproduce it. Then I'd encourage you to maybe explore another model or two. But we're going to take a detour and finish up this with another example. And this is an example of response surface methodology in practice. This comes from the Journal of Optoelectronics and Biomedical Materials from 2010. And it's a problem. The title is Optimization of Cell Death Using Response Surface Methodology of the Effect of Time and Concentration on a Particular Compound Photosensitizer. Now, I'm not going to read the abstract. We'll leave this here for you. But the part that's important for us is this is an application of using response surface methods to evaluate the effect of 2 parameters, the time of exposure and the concentration of this particular compound on the viability of two cell lines. Well, first cell line is called MCF7, the second is T47D, and both of these cell lines are breast cancer, breast adenocarcinoma cell lines. Right? And this is an optimization problem. So you want to try to optimize the time of exposure and concentration of exposure, right, to kill off these cells. So this is an example. The practical problem is radiation treatment for breast cancer. We're targeting two specific cell lines, and we're using a tracer, and we're exposing the patient to radiation for some amount of time. Okay. And the abstract gives you additional detail about the energy dose and the concentration of the photosynthesizer that's used. So you have maybe an upper and lower bound on the time, you have an upper and lower bound on concentration, and you're looking for an optimal in that range, because you don't want to expose the subject to too much radiation, and you don't want to expose them to too little, because that's not effective treatment, and then it'll maybe prolong treatment, eventually exposing them to too much radiation. And so there's a real need to try to optimize the exposure to determine the most effective treatment for the subject. So it's a little bit of background. So we're talking about photodynamic therapy. It's a way of treating cancer. We're using a drug called a photosensitizer, and the photosensitizer that's used is targets a specific cell type or a cell line that's in the tumor, and that's differentiated from the surrounding tissue. So you inject the light-sensitive drug and then expose them to radiation. Right. So the main effects of the drug depend on concentration, incubation time, oxygen present in the blood, the lifetime of the molecule, of the light-sensitive, the photosensitizer itself, and other factors that are not germane to our particular interests. Okay. So this particular study is an attempt to use response surface methodology to find the optimal operating conditions of time of exposure and photosensitizer dosage to be effective in eradicating the tumor cells. Okay. So here's an absorption spectrum for the photosensitizer, right? And here you see, wavelength. The three different lines here represent different concentrations. And the question for us as maybe the biostatistician assisting the clinicians in this study would be to develop the methodology to find the optimal operating conditions. Okay. So here's the experimental design. So this is our original response surface method response. The response variable y, two factors, time and concentration. And if you read the paper, they use a central composite design with two independent variables that are x1 and x2. 13 runs were used for each of the cell lines, and to cover all possible combinations of the factors that were used. So you might start with an additional, with an original factorial design and then add a central composite. Now we haven't said whether they're axial or whether this was a face-centered, but suffice it to say, let's assume the most general case of a central composite design, so some were on the face, some were beyond. The data were from the original two-factor experiment, 5 center points and 4 axial points. And of course, as we all know by now, one of the 3 R's, you randomize the order of the experiments to minimize variability in the response. So here's the second order model, or another way of representing the second order model. So x1 and x2 are time and photosynthesizer concentration. And so here's the intercept term. This is the normalized response variable. This summation, right, the summation from 1 to 2, represents the first order term, what was called FO, in the RSM package. This is the pure second order terms, PQ. And then this summation, where I is less than j, is the set of the two-factor interaction terms, where I is strictly less than j, so it's I1, I2. If I had more, this would be I1, I2 plus I1, I3 plus I1, I4 if this was the helicopter problem, right? But although represented differently, recognize this as a second order surface with first order, purely quadratic, and the two-factor interaction terms. Here is the relationship between the external and extrinsic and intrinsic coordinate system. These are the intrinsic variables. This is the extrinsic variable. So Ci is the natural, or the natural coordinates. High level and low level are the dynamic range of that particular variable. So if you take the data that's in the paper and you use RSM to fit the models for each of the cell lines, these are the second order models that you get. So here's the intercept of time. These are the coefficients for time and for concentration, the purely quadratic terms and the single interaction term for the cell line MCF7 and for cell line T47D. This page is a reproduction of the analysis of variance from the actual manuscript. And this is for the cell line MCF7. So the column is sum of squares, degrees of freedom, mean squared, F value, P value, just as we know, analysis of variance. And the possible sources of variation are model, time, concentration, time squared, concentration squared. So these are the pure quadratic terms, linear terms, quadratic terms, and then interaction term, residual, and error. Okay, and what you see from the p-values is that they're all significant, right? The p-values happen to be wrapped around. So all are very, very small, saying that anything from the model through time, concentration, or the other terms explain the observed variation. Here's the same thing for the T47D cell line, the analysis of variance. Same thing, model, time, concentration, purely quadratic, two-factor interaction terms. What's evident here is that so here's purely quadratic time squared, still explains the variation. One can assume from this that concentration does not, and it's unlikely that the two-factor interaction term does not explain, or at least that's how one would normally interpret these results. Right? Here's the response surface plot for the MCF7 cell line. So this is the factor time of light exposure, factor concentration of the photosensitizer. Right? You see constant curves, constant values of the response. This response surface plot for the MCF7 cell line shows time along this axis, concentration, and this is the response variable, viability. So this is viability of the adenocarcinoma cells, MCF7. Now, we probably all know that our interest, if it's cancer therapy, would be in minimizing the viability of the cells. And so we're looking here for a minimum rather than a maximum. So we want to minimize the viability.